Hi. So, in this episode, I would like to talk about EVS or event-based cameras. They are very interesting cameras. I would say it's a very interesting technology to which is a little bit or completely different from the normal camera systems, which are basically frame-based cameras, and they have pixels. Unlike them, EVS or Neuromorphic, I guess it's called, or event or in marketing EVS cameras, they are basically they basically work based on illuminance and thresholds, and basically the way that they function is dependent on the threshold that is defined for the regulators to accept or reject the signal. So we will go through this website, which belongs to Sony. Sony has recently launched a product which is a EVS cameras and EVS sensors. EVS stands for basically event-based vision sensors, and basically realizes high-speed data output with low latency by limiting the output data to luminance changes from each pixel combined with information on coordinate and time. With a focus on movement, they can be applied in a wide variety of application or fields. So basically there's plenty or enormous application for EVS or event-based cameras. They are actually very similar to the way that our eye and or vision system actually works. In here, for example, you can see that our human eye has a rod cell, which is basically converting somehow or gets the light inside, and then we have bipolar cells for the second stage, and then we have retinal ganglion cell. I hope that I pronounced it correctly, which is a kind of medium to the cortex in the brain, or visual cortex in the brain, to transfer the signal. So exactly the way that our eye or human eye functions, EVS also is like that. So there is a light receiving unit which basically convert energy or photon energy to voltage, basically, or current to voltage, and then it converts. In the second stage, we have an amplification unit, and the third is a comparator, which basically you will define a threshold, and then if that amount of let's say signal amplitude reach to that level, over that level it will be a plus event, and below that level it will be a minus event. And in this way you do not basically capture everything, only those asynchronous points or cells that has received amount of value or amount of energy as an input that basically goes beyond the defined value of the threshold, will give a positive value. So we have either 1 or 0. If it is more than threshold, then it will be positive plus, and will be represented in the system as a plus signal. And if it is below that threshold, then we have a minus, and that's nothing. So nothing appears in the picture or in the image. So this is the general format or structure of these sensors. And then the mechanism is, as you see in this, I hope that you can see, yeah. So the mechanism that this is, see, imagine that there is a ball moving in front of you. What is this capture is nothing, just only ball. So any background that the sensor is focused and is static has no value for the sensor. Only that object, for example here as a ball, in each pixel will be represented as a dot, and the position of this ball it's clear that it changes over the time, and it moves from one position, XY position, to the next position over the time. So we have a continuous traction or detection of the ball movement over the time without any stop. And as I said, the beauty of these sensors is that they just only focus on the motion or movable objects. So here there is a better explanation a bit. So yeah, so the pixel units basically attracts or absorb the light, and then it will be converted to voltage. And the next step, we have a delta modulation, which in delta modulation you will compare as a reference that you have defined the value, the reference voltage and the output voltage from the pixel unit. So you have to detect or compare this delta, and if this delta is more or exceeds the defined threshold, then an event plus will be generated. If not, it will be minus or nothing. So the idea or the concept is based ratherly easy, but the applications are quite interesting. The next one, there is also very interesting animation. As you see, you have a high threshold, a lower threshold, and a reference voltage. So as much the threshold for the illumination of this pixel is below the reference, the event signal is negative. So you will see it here as a blue arrow keys toward down. And when it goes up and reach to the level of reference voltage, then the positive signal of event will be created. It is very fascinating actually. So you can actually define as well the threshold. It depends on your application. If you are in a very maybe noisy environment, or there is a huge of exposure, might be the reason to change the reference voltage, but generally it depends on that. And the next, another, as I said, one of the benefits of EVS over frame-based cameras is that frame-based camera in exposure light, they get blurs, and it's quite hard to detect any object for these cameras. But for EVS or event-based cameras, it's not like that. As you see, it doesn't matter how much the luminance changes, always the output voltage or delta V is the same. And that's a great benefit to detect in any circumstance, also any condition, any light condition, to detect the value of the object. And that's a great benefit or is very robust, I would say. Without any post-processing, you can get these values, and it's very worthy. So the next, there's this picture that you see at the left and right. So frame-based image sensor, you can see such a thing at the left, and EVS sensor you can get. Basically, if I want to be honest with you, is very similar to yeah, the method of edge detecting by a normal webcam or camera. So but the only difference is that as I said, objects should be moving in EVS to be detectable. Otherwise, I mean, like as I said, for frame-based image sensors to get such a thing, you need to put a lot of high computational power to apply methods like Laplacian, for example, to get the edge to detect the edges. But for EVS, it's already there without any post-processing. Sony claims that they have special copper to copper technology to make even the chips smaller. So basically, what I have seen is that in conventional basically way of chips production of sensor, basically so it's unlike conventional technology that has the light receiving circuit and luminance detection circuit on the same layer. This technology incorporates them on different layers, a pixel chip as an upper layer and a logic chip as a lower level, which includes integrated signal processing circuits. So they can basically reduce the size of the chips with the parallelization of the layers, and that has a great benefits for bigger production of the chips with higher coverage of the scene, basically this or field. So these chips are stacked and connected using copper to copper technology within each pixel, as I said. At the moment, I think that the industry's smallest pixels is about 4.86 micrometer. Is integrated with the logic chips on a 40 nanometer process, resulting in a 1 over 2.5 type sensor with HD resolution of 1280 in 720. All right, so from it seems that we have much more compact design. And because of this compact design and because of this the instinct, the base of this technology, there is a high speed of computation and also lower latency. So because each pixel detects luminance changes asynchronously and will output event data immediately. So there is, as I said, there is no really needed for any post-processing. This is also interesting, and built-in hardware event filter. Sometimes because of the LEDs flickering in the event EVS sensors, there is a need of filter. So as you see in the left picture, it is taken by event camera. You will see a lot of noise, I would say, in the image. But if you put on the filter, you will see that basically those events are much more clear. I'm very surprised. I don't know if you can see that here, but this looks like an autobahn to me. And at the left side, if this is the guardrails of the autobahn, I could imagine from the left side I cannot really see anything or detect any object. But when I look at the right, exactly at the same corner, I kind of see or notice a car, which at the left side I can't see that, but at the right side it is there. I see kind of like a car. But I mean, like, it is quite interesting, huh? Because you can really detect a lot of movable or useful data without any kind of computational power for post-processing. I would like to show you an application video that actually belongs to the Sony instead of the pictures. So as an examples, so let's review this video together. I hope that you can see that. Okay, yeah. So this is somehow, I guess, the applications of this. I hope that I have chosen the right. Yeah, I guess I have chosen the right video. So as I said, any movable object can be detected exactly like our eyes process an image. The event-based vision sensors also process that. So you see that this ball that I talked about in basically a frame base or conventional frame base, you have a lot of pixels taken, but it's not a continuous. But at the real time or event base, you have this continuous follow up from the position, and that will be created, as you see in this photo, that exactly the route or the track that the balls goes will be recorded. You have the position, you have the time, you know that where was the ball at what specific time, which in basically frame based you cannot really follow up at what frame, or maybe it's where was the position. So it's also, and I also talked about this chip technology that they have integrated and make it compact, everything parallel, the processing units parallel to the detection unit, and everything integrated much more compact from the copper technology that they have follow up, and makes it possible to aperture ratio without any loss, to increase the aperture ratio to the entire sensor, and reduction of the circuit and and making a lower latency. And so this ball was one example. And as I said, the incident, it doesn't matter what is the exposure situation in the image. It is always the amount of output voltage. Doesn't matter what is the situation, it will be the same basically with the camera. So that was unfortunately the wrong that was the first video. I think this one was about the application. Hopefully, yes. So this is, as I said, a review about that. What are the application of event camera? The first one, as you see, there is the frame base camera is a flow of water, and the event base is just representing each single droplets of the water. You can exactly detect and position that, and that's beautiful. And it is very super in a super slow EVS. You can see the amount of each droplets. The next one is human tracking. At the left side, you have a frame-based camera. You see how difficult it is for the frame-based camera to detect the person when it is very dark. But at the right side, you see that it is quite obvious. Even the position, the way it's continuously, it's not really sensible to the darkness of the colors or whatever. So it was in metal processing, for example, monitoring the sparks. It's also another application or example. You see at the right side, all these small sparks can be detected and followed up, and the amount of or the number of these sparks can also be summed up. This is also very interesting application. You see that there is a band or conveying layer. There is one object moving up, usually could be very dark. There is a laser which is perpendicular on that, and there is a camera installed on the left side. So camera look at the basically the box and the temporal information, and also the laser line which is on the band and also on the so you see on the band, and also the again I would say just hope, yeah, you see that at the right side, the laser, there is a difference between the baseline and the BOSC, and you can see that you can probably measure the height differences. And it is not only about the height, but also visualization of a 3D model of this box. That's the beauty, because you kind of get an estimate of the height of the object, but from the other side, the EVS can create a temporal cloud of points related to this box. And it's not only about the height difference, but also about the shape, the 3D shape of that box. As you see up the right side, you can get exactly the format of the box, and that will quite help a lot to later with machine learning tools to detect the real object. Here it is also very interesting. The left side, there is a frame base. The platform actually is vibrating. You don't see anything different. It's very hard. But at the right side, application output, you can change the frequency from low frequency to high, from 30 hertz to anything. So this is very, very, very interesting. I would like go back again. This It is basically with frame base. It's not really easy to detect, but with the right, you can see that there is actually a vibration happening, and this was really cool. I like that. And vibration is actually for a lot of maintenance in the machinery a big factor, which using such a camera can actually trigger if the construction, something is not right, or the structure is basically under pressure or something like that. Yeah, so this was some application overview of this frame. I honestly, I don't think there are too many event-based cameras available in the market. I've seen this one from Sony, EVS sensors. The other one was from Prophecies or something like that. I don't remember, but not, as I said, not many companies and models of EVS at the moment exist in the market, but I think they will be get common quite well in the future. So there is also another examples, like for example I would say application in the industrial automation, especially vision for detection of faults and errors in construction or products, can also visual inspection, basically contamination of detection inspection. This is also another field that can be applied if the material has been changed or if there is any damage. This is also, so their small data size and compatibility with machine learning are also notable features. With the RGB camera, the way scratches are perceived will differ depending on the way color appears, so the data volume will become larger. Comparatively, EVS detects differences in luminance for each pixel and only use the differential data for output after combining it with coordinate and temporal information. So the data is small in size and high in output speed. So the difference is here is that if you use a normal frame-based RGB camera, a lot of information comes and you need to do post-processing in order to detect the cracks or whatever that is somehow making a problem here. But the EVS goes directly to those differences and shows you the cracks directly without any post-processing. In meshing abnormality detection, also exactly the same. So you can detect the abnormality by the output data, which is small in size and no latency, and detect the abnormalities. In robotics, of course, the robots moves, and of course it's much easier to detect the edges, and when it is in motion, of course that's easier for the robot to detect, and especially in logistics or transport or home delivery, I don't know, with drones for example. A lot of things can be processed with a very, very little computational power that takes by normal frame-based cameras. And yeah, so for example, for monitoring the people and a crowd, usually with frame base you have to take a lot of data. You probably save a lot of data from the face, which is sometimes not suitable because of the data privacy. So if you need just the location of the people, you can use EVS, and just without getting much information from the picture appearance of the person, it can be data privacy, has a better data privacy. In scientific measurement, of course, in investigation, EVS is applicable to scientific measurement, that it can detect high-speed moving object in a field of customer behavior investigation. This is actually something that I personally would like to try it, but unfortunately I do not know anyone who can lend me an EVS camera. Or it's actually, it is very expensive. As I said, I take a look, it's about 5,000 euro for a small EVS camera, which I cannot afford it at the moment. So but if I could that, I would definitely try to measure or repeat these experiments that are done by young, because of this interference of or quantumal behavior of photons by young experiments, and use these EVS cameras to detect the motion of the photons when they are crossing from these two slides, to see how these photons actually interference with each other, because it's very close to how our eyes can understand or perceive, how to say, analyze this scene. So if you have a detector, unlike the frame-based detectors, this could be somehow have an interesting result. I'm not sure, just guessing. And the last is that the UI UX development, of course, there are a lot of tools available in open source community or software that you can actually use your gesture to have conversation or connection with machines, of course. And EVS is a very nice platform to ease this process for the human to get connected with the machines. So this is also another potential application for EVS. All right, I hope that you guys enjoyed this episode. If I can get in future an event-based camera, I will definitely make an episode about that. But I hope that you enjoyed it. All right, have a good weekend. Bye.